Hello everyone, welcome! Today we're diving into derivatives, a cornerstone of calculus that might seem intimidating at first. But trust me, it's incredibly fascinating. It's a powerful math tool for understanding change, a concept that governs everything around us. Look around. Cars move, constantly adjusting their speed. The sun rises, marking the passage of time with its ever-changing position. Plants grow, transforming from tiny seeds to towering trees. Change is everywhere, an undeniable force shaping our world. Derivatives let us measure how fast things change, providing a precise way to quantify these dynamic processes. Whether it's speed in physics, calculating the acceleration of a rocket, profit in economics, predicting market trends and optimizing investments, or population in biology, understanding how populations grow and evolve. This isn't just textbook math, it's so much more than that. It's a lens to see the world's hidden patterns, revealing the underlying mechanisms that drive change. Before calculus, people wondered, they grappled with the challenge of, how fast is something changing right now? At this very instant? Newton and Leibniz answered that, independently revolutionizing mathematics, inventing derivatives and launching modern science, paving the way for countless discoveries. Learning derivatives is like upgrading your vision, sharpening your understanding of the world. You'll see not just what's happening, the current state of affairs, but how fast it's happening, the rate at which things are evolving. When you look at a graph, you'll ask, how steep is it here? What's the slope at this point? Is it speeding up or slowing down? Is the rate of change increasing or decreasing? Let's explore this idea together, step by step, and unlock the power of derivatives. So, what exactly is a derivative? It's a fundamental concept in calculus, but what does it really mean? Simply put, it's the instantaneous rate of change. Think of it as capturing a snapshot of how something is changing at a specific moment in time. Imagine a road trip. Your average speed is easy to find by dividing the total distance traveled by the total time. But the derivative tells you your exact speed at any moment. It's not an average, but a precise value at a single point in time. It's the number on your speedometer. That number isn't an average, it's your speed at that very instant. Mathematically, a derivative finds how one quantity changes in response to another at a specific point. It allows us to analyze the relationship between variables with incredible precision. On a graph, it's the slope at a single point. This slope represents the rate of change at that exact location on the curve. For a straight line, the slope is constant. It's the same everywhere along the line. But for a curve, it changes everywhere. The steepness of the curve varies from point to point. The derivative lets us zoom in on a curve until it looks straight, allowing us to analyze its behavior at a microscopic level, then measures that tiny slope. This tiny slope is the derivative at that point. So remember, a derivative is both the instantaneous rate of change, capturing the speed of change at a specific moment, and the slope at a point. It's the steepness of the line tangent to the curve at that location. These two ideas are the heart of what a derivative means. They are two sides of the same coin, offering a powerful way to understand change. It's a precise tool for measuring change, giving us the ability to quantify how things are evolving, right when it happens. It's not about predicting the future, but understanding the present with clarity. Whenever you hear derivative, think, how fast is this changing right now? What's the rate of change at this very instant? That's the magic of derivatives. It unlocks a deeper understanding of the world around us. Derivatives are a mathematical superpower. They help us analyze and predict. In business, they show where profit peaks or costs drop. In physics, they turn position into velocity and velocity into acceleration. With derivatives, scientists chart rocket paths and predict planetary motion. In math class, derivatives reveal where a function rises, falls, or reaches a peak, making graphs easier to understand. They model real-world changes, temperature, money, health, all described with derivatives. Learning derivatives is like unlocking the code behind how the world works. All right, let's dive in and see derivatives in action. We've talked about the theory, but now it's time to get our hands dirty with some real examples. This is where the abstract becomes concrete, and you'll start to see the power of this mathematical tool. We'll begin with some simple examples. These are designed to be straightforward, so you can focus on understanding the core concept without getting bogged down in complicated algebra. Think of this as building blocks. Let's start with a classic. For y equals sine 2x plus 3, a simple linear equation. In this case, the slope is always 2. No matter where you are on the line, for every 1 unit you move to the right, you go up 2 units. constant rate of change. Now let's consider y equals sine 5, a flat line, representing a constant value. Since it's a horizontal line, the slope is 0. There's no change in y as x changes. Consequently, the derivative is 0. This makes sense, right? No change means no derivative. This illustrates a fundamental rule. The derivative of any constant is always 0. There's no change, no slope. It's a static value, completely independent of x. Now let's try a curve, y equals sine x2. This introduces a bit more complexity, as the slope is no longer constant. Using the power rule, its derivative is y equals sine 2x. Notice how the derivative is now a function of x. This means that at x equals sine 1, the slope is 2, and at x equals sine 0, it's flat, slope 0. The tangent line is perfectly horizontal. Furthermore, at x equals sine 3, the slope is 6, steep and downward. The negative sign indicates the function is decreasing at that point. What's really cool is that the derivative gives you a formula for the slope at every point along the curve, not just one specific location. So instead of just having one slope for the whole function, like in our linear example, you get a new function, the derivative, that tells you the slope everywhere on the original function. And that's the core of derivatives. It's a powerful tool to measure change, or the rate of change, at any specific point on a curve or function. Understanding this foundation will be incredibly helpful as you tackle more complex and interesting problems ahead. As we wrap up, remember, learning derivatives is a journey, and it's normal to find it challenging at first. We saw that derivatives measure change, as both instantaneous rate and slope at a point. They're used everywhere, from science to business, to analyze and predict. Focus on the core idea. A derivative is just a slope, a rate of change. Every new rule you learn is just a shortcut to find that slope. Stay curious, be patient, and celebrate your progress. You're ready to unlock one of math's most powerful ideas. Good luck!